Hi, in this video, we want to talk about friction. So we'll be looking at the meaning of friction, we'll be looking at the types of friction, we'll be looking at the laws of friction, then how we analyze questions underneath friction. So what exactly is friction? The friction is simply a type of force that acts at the surface of separation between two objects or bodies in contact. So when we have a force that acts or always acts at the surface of separation between two bodies or objects that are in contact with each other and tends to oppose the motion of one over the other, then we'll talk about friction. So friction is simply a force that opposes motion. But before it can oppose motion, there must be a separation between two objects or two bodies. They must be relative or moving relative to each other. And my friction or friction would always oppose the motion. So we have two main types of friction. We have the static friction, which we are going to be denoting with F of x, and then we have the dynamic friction, which we are going to be denoting with F of d. Now, f of x will always be greater than f of d. We are going to know why shortly during the course of the video. But moving on, let's talk about the laws of friction. The first one that we should be familiar with is that friction opposes the relative motion of two surfaces in contact. Friction opposes the relative motion of two surfaces in contact. Friction is independent of the area of contact between the surfaces. That is, friction doesn't care about the area of contact between the surfaces. It will always act in opposition of one motion towards the or against the other. So it is independent of the area of contact between the surfaces. Number three, friction depends on the nature of surfaces in contact. That is, if the surface is extremely smooth, then it means there will be little to no friction. And then if the surface is extremely rough, then friction will be extremely high. Number four, friction is proportional to the normal reaction acting on the body. Friction is proportional to the normal reaction acting on the body. And lastly, friction is independent of the relative velocity between the surfaces. Friction is independent of the relative velocity between the surfaces. That is, doesn't care how fast an object moves, so it will still tend to act. Now, before we look at what the laws actually mean and why my static friction is greater than my dynamic friction, let's imagine an object being placed on a ground, be it an horizontal ground or a vertical ground. So you have this, and then this is my ground. Now, this object will, by virtue, feel two forces that are fundamental. So, fundamental in the sense that all objects, whether a person, a living thing, or a non-living thing, your vehicles, your school bags, your laptop, your phones, all feel these forces by virtue of being in the Earth's gravitational pull. And which forces are we talking about? We're talking about our weight force, which is always pointing down, W. And then, by virtue of Newton's third law, for every action, we have an equal but opposite reaction. So we feel a normal reaction always pointing up, and then we call it our R. Remember, from our laws of friction, we say the frictional force is always proportional to our normal reaction of the body. Why that is true, we're going to look at it soon. Now, if this is clear, then let's move on to another concept. Now, when we have, so we're going to be using this box again, this box to analyze this. So imagine I were to apply a force of, so a force in this direction, FA, applied force, and then I have my frictional force opposing this. So I'm going to start with Fs. Because remember, we said Fs means static friction. Static friction. Now, since I'm applying the force in this direction, I'm applying the force on my box, and my box has, is separated by is in contact with my ground rather, and then since it is in contact with my ground, it's going to experience some form of friction in the opposite direction to this applied force. Now, if I'm applying a force of 1 Newton, so let's say I apply the force of 1 Newton to start, I notice that my box didn't move. If my box didn't move, I can deduce that it must mean because my applied force is equal to my static friction. Now, this is the only instance where this box will move. Because if my applied force is greater than my static friction, then definitely my box should move. But for my box to remain stagnant even after applying a force on it, and it still didn't move, then it must mean that my applied force is equal to my or the static friction. Now, after seeing that the box didn't move, I decided to increase my force to 2 newtons again. The box didn't move, so it must mean that F is still equal to Fs. That is, my applied force is 2 newtons, my static friction should also be 2 newtons. 3 newtons, same thing, my box didn't move, so F is equal to Fx. 4 newtons, same thing, my box didn't move, F is equal to Fx. Then, when I applied a force of 5 newtons, I discovered that my object just started moving at the verge of moving. Now, when that happens, I can sketch this on a graph. So if we're to plot applied force to that of friction on a graph, we'll have something like this. So I have my applied force on the x-axis, applied force on the x-axis, and then I have my frictional force F of x on the y-axis. Remember what we said, when our applied force was 1 Newton, my static friction was 1. When applied force was 2, my static friction was 2, and then up until we get to 5. So let's try and calibrate this. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 1, this is 2, 3, 4, 5. So when my applied force was 1, my static friction 1, applied force 2, 2, applied force 3, 3, applied force 4, 4. Now at point 5, when I was applying a force of 5 Newton, we said our object is just beginning to move, So at this point 5 here, the friction I can feel, or the static friction I can feel, is maximum. If it is maximum, I can say Fx max will now be directly proportional to R. Remember what we said from our law, the frictional force is always directly proportional to R. The frictional force remain is the maximum static friction, always directly proportional to R. If it is not the maximum static friction, then my applied friction, or my applied force rather, will be equal to my static friction, in as much as my object is at rest. Now, to remove this constant of proportionality, first of all, we try to complete our graph. So if we complete this graph, we discover that this graph is looking like a straight line graph. And we know that the constant of a straight line, or the slope of a straight line graph, would always be constant. If that is constant, then we can remove our constant of proportionality. And that constant, we call it our coefficient of static friction. So Fx max can now be equal to mu s r, so the coefficient of static friction times r, where r is equal to w and w is equal to mg. We talked about this in the previous diagram. Now we are going to be looking at how to analyze questions underneath static friction and dynamic friction. But before we do that, when we started talking about friction, we said our static friction will always be greater than our dynamic friction. So why is that? Now what happens when I increase my applied force to 6 newtons? So you notice that my frictional force, instead of moving higher, it goes lower to maybe a point like this. And then if I keep on increasing the forces I'm applying, 7, 8, 9, up until infinity, my frictional force just keeps going in this direction. So that's because it's going to take more force to make an object move than keep that object in constant motion. So that's why static friction would always be greater than dynamic friction, in as much as we're talking about the maximum static friction. All right, so now in an attempt to analyze questions underneath static frictions, we are going to be looking at three different cases. The first case, when my object is purely horizontal or placed on an horizontal ground like this. So we have a box of mass M placed on an horizontal ground, and then I'm pulling the box horizontally. The force I'm applying is parallel to the ground, not inclined at an angle, not perpendicular to any particular or to the ground rather. Then how do I analyze this? So the first thing I want to do, or the first thing you want to do when you're giving questions underneath this, is to write the two forces acting on this box naturally, which is the weight of the box, W, and then we have the R. Then if we've written these two, then we can now come and say we have an applied force moving towards the direction you are pulling, and then frictional force will be the last force we want to represent, Fs. So I'm using Fs because we're assuming that this object is not moving. Now, once they give you questions underneath this, that the object is not moving, you know that your Fa will be equal to Fs. You always take your applied force to be equal to Fs. And we already know that static friction will be equal to mu s of R. So this is the formula you want to be familiar with when you're analyzing a static friction box placed on an horizontal ground, and the force being applied is parallel to the ground surface. So it will be tested beyond this. Now, what if our box is still horizontal, but this time around we're applying an inclined force in such a way that it looks like this, being put in this direction, and then we're giving this angle to be theta. Now this angle is theta, and then this is my applied force. Then again, I'm going to draw my weight pointing downwards, and then my reaction pointing upward, R. And then lastly, I'll draw my frictional force pointing in this direction. Here, horizontal to the cause of motion. Now, this FA we are given, we want to resolve. Of course, you guys have not been taught vectors yet, but subsequently, I'm going to be releasing a video on vectors, and then we'll learn how to resolve forces into their components. But for a case like this, in as much as they are pushing or pulling the box, rather, not pushing, pulling the box at an angle, then you can resolve this force in this direction. So if we have it going up, it means I have a force going towards the right, and the force going towards the right, I'll call it Fa cos theta. Then the one going upward, I will call it Fa sine theta. So all these things are gotten from our resolution of forces underneath vectors. But we want to make sure we're familiar with Fa cos theta, which is the force responsible for moving the box horizontally. Fa sine theta has no effect on the box moving horizontally. So it just acts to balance the weight of the object. So if we are to derive our equation or generate our equation from this, I can now say Ff must be equal to Fa cos theta, and then since Ff is mu r, then I can say mu r is equal to Fa cos theta. This is one formula we want to be familiar with. Then also, peradventure we're looking for the R, or we're looking for W, or we're looking for mass of the what's it called? The mass of the box. We already know that W is equal to mg, and this is equal to R. Then if we're okay, so this won't be equal to R anymore because we have two forces that are pointing upward. So instead, to be equal to R plus Fa sine theta. So these are the formulas we want to be familiar with for a force that is inclined at an angle and then pulling my box horizontal. Now the last analysis of our question of static friction will come underneath when my box is now placed on an inclined plane. So if you have a box placed on an inclined plane, how do we analyze that? So let's say we have a box in this direction. So I have my box on this inclined plane, and then I have something like this. So this is my angle theta. Now, if this is my angle theta, remember the two forces that we say always act on the box by virtue of being in the Earth's gravitational space is my normal reaction pointing upward, always pointing upward, and then my what's it called? My weight pointing downward. So let me draw this properly. Let's draw this properly. So this is theta. Let me try to remove this. All right, so now I have my weight pointing downwards in this direction. So let me call this mj. All right, so now I can call this theta at an angle of theta. Now, if we were to look at this, how to analyze this again, we got this from our knowledge on geometry and vectors too. Now, if I were to assume that this is purely my x-axis, sorry about that. This is purely my x-axis. This line I've drawn here is purely my x-axis. Of course, this will be my r. Now, I want to assume that this place where my r is, since my r is pointing upward, this line I've drawn will be my y-axis. Now, if that is true, if this is theta, then definitely the angle between my weight and the y-axis I've drawn will also be theta. Then, if you can see, r is looking purely vertical, but my weight is looking like an inclined force in this direction. So if that is true, we want to resolve the same way we resolved the last one, the last question. So we know that the one that is pointing down in this direction here would now be, so this time around we're going to switch. We'll be switching our, what's it called, our sine ratio or trig ratios. So the one pointing down, we want to call it our mj cos theta, and the force responsible for making my object come in this direction. So if my object is sliding down, I can call this force, mj sine theta. Then I can put my frictional force in this direction. But this only works if my object is sliding down. If my object is being pulled up, or like I'm applying a force upward, not being pulled up now, so then my mg sine theta will be in the opposite direction, and then my frictional or my friction fs will be in the opposite direction. I hope this makes sense. All right, so this is all for static friction. Now for dynamic friction. So for dynamic friction, again, we're going to start analyzing with the same approach or with the same example that we did for static friction. When we have a box that is placed horizontal now, so this time around, instead of the box to remain static, we assume that the box is moving. So I have an applied force in this direction. I have my weight pointing downwards, W, pointing downwards. I have my arrow going upwards, arrow going up, and then I have my frictional force in this direction. So this time around, I'll call my frictional force F of D. In some textbooks they use F of K, it doesn't really matter, it's just the naming. Now, since my object is moving now, so I can say, before my object must move, it must be that I have a net force that is being applied on the box. So what do I mean by net force? Let's assume that when I applied 5 newtons, we said underneath static friction, we said my object is just about to move. So I can say that my applied force is still or slightly equal to 5 newtons. Or if I don't want to say that, imagine when we're talking about 4 newtons. When I applied the force of 4 newtons, we said my static friction was 4 newtons. Now let's fast forward to when we applied a force of 6 newtons. 6 newtons, N, this is N. Now, the force responsible for making my object move is not this 6 newtons. Remember from what we said, from 1 newton, my static friction is 1 newton, wasting our effort. 2 newtons, static friction was 2 newtons, wasting our effort again. 5 newtons is just about to move. So once I get to 6 newtons, it means my box is moving with the net force of 1 newton. So if I have a net force, then definitely it changes the way we analyze our question. So we want to analyze this question including that net force that is responsible for making my object move in this horizontal path. Now, if we're going to do that, then we can now say, since my object is moving towards the right, then definitely my FA now is greater than my FD. So I can say FA minus FD must be equal to F net. So that's the first equation I want to write, where F net is simply equal to FA minus FD is equal to MA. So this is how I want to analyze this. Remember, you'll be given the applied force. FD here is simply equal to coefficient of dynamic friction on mu K or mu D times the normal reaction. So these are the two equations that you want to be familiar with, in as much as you have an applied force that is horizontal and also parallel to the horizontal surface. But what if you have a force like this that is inclined at an angle like this, and then here we have theta here. Okay, so if you have theta here like this is my applied force FA. Then I'm saying my box is moving towards this direction, and then I have my weight coming down, W coming down. I have my R going up, R is going up, and then I have my frictional force going in the opposite direction, like this FF. So how do we analyze this? Again, we want to resolve this force FA. So I know that towards the right, I have FA cos theta going upward. I have FA sine theta. Now, if I have these two forces, the one responsible for making my object move in this path will simply be FA cos theta. And I can say FA cos theta minus the frictional force Fk must be equal to F net, where F net is equal to MA. So this is the first equation I want to write underneath this. And then also I can say my Fk will be equal to mu R plus Fa sine theta. Fk is equal to mu R plus Fk sine theta. So Fa k is equal to mu R plus Fa sine theta. So this is the second equation I want to write. Oh, sorry, we shouldn't use sine theta. Sorry about that. This is not this one. So Fk is simply equal to mu R. So it is R, or it is W rather. So W that will be equal to R plus what's it called? Fa sine theta. So this is the correct equation. So equation 1, equation 2, and then equation 3. So when we're solving questions, we are going to be applying all this logic. So lastly, when our box is on an inclined plane, so when it is on an inclined plane, how do we analyze the question, especially when we're dealing with dynamic friction? So to analyze this, let's try and draw a diagram. So I have a diagram here. So I have a box in this direction, and then this is my angle theta. So my box is pointing down. Let me call this mg, which is my weight, and then this is going up. Let me call this my r. So again, we already know that. So if my box is being pulled up in this direction, if my box is being pulled up, so let's say by a rope, so definitely I can feel some tension in this rope, then my mg sine theta will be in this direction. Mg sine theta will be in this direction. Then my frictional force, since I'm pulling the box up like this now, my frictional force will also be in this direction. Frictional force will be in this direction also. So frictional force will be in this direction. So this time around, I have two forces that are opposing this tension or this force that is being applied here. So to analyze this, what I simply want to do is to say my T minus mg sine theta minus frictional force must be equal to F net. But most times when we encounter questions like this, that we have tension, or a rope being pulling my object up and so, they will ask us to neglect friction. But just in case you don't have to neglect friction, you simply analyze in this way. So, and also you can get your angle theta by just taking the, sorry about that. So you can get your coefficient of dynamic friction mu by simply taking the tan of theta. So this is gotten by when you derive your two equations. Remember, we have an equation going pointing down. So if that is equal to r, divide both sides of the equation by what's it called, by each other. So sine theta divided by cos theta, we're going to be ending up with tan theta, and hence we can find our coefficient of dynamic friction by just taking the quick function tan of our angle theta. So I hope this concept is clear. So now we'll be moving on to the questions underneath friction. So for our first question, we're given a metal block of mass 8 kg lies on a rough horizontal platform. If the horizontal resistive force is 10 newtons, find the coefficient of static friction. Now, one way to be extremely good in analyzing questions on friction is to always draw a free body sketch or a free body diagram. So I can simply say this is my metal block rather, of 8 kg. So this is 8 kg, lies on a rough horizontal platform. So because they say it is rough, we know it has some form of friction. If the horizontal resistive force is 10 newtons, so this time around, they're giving us the magnitude of our frictional force. So we can say, so if this is, let me draw the line perfectly. So if this is my frictional force, f of x, so we say it is equal to 10 newtons. So it must mean that perhaps I'm applying a force in this direction. Find the coefficient of static friction. So now we're looking for the coefficient of static friction. So what do we know? On this box alone, I have my weight pointing down, and then I have my normal reaction going up, R and then W. So we already said W is equal to mg. So this time around, we're going to be taking G as 10 meter per second squared. So that will be 8 times 10. And then that will give us 80 newtons. Now, after getting W, I know W must be equal to R. So if W is equal to 80 newtons, definitely R also is equal to 80 newtons. Now, to find the coefficient of my static friction, I simply want to say Fs must be equal to mu S R. So remember, I'm looking for mu SR or mu S rather. So make mu S the separate formula, divide both sides by R, divided by R, divided by R. Then mu S must be equal to Fs all over R. So R cancel R, R cancel R, and then mu S now will be equal to, what's my um friction or my static friction, that's 10, and then what's my R, that's 80. So 0 here, 0. So mu S or my coefficient of static friction would now be, so that's 0.1, 0.12. So I think that's 0.12 recurring. So that would be our final answer, 0.12 units. So it has no, its dimensionless, it has no dimension. Moving on to the second question. All right, so for the second question, we're told that a metal block of mass 0.5 kg lies on a rough horizontal plane. Find the normal reaction. So again, we just want to sketch a metal block lies on a rough horizontal surface. This time around, we're not given the frictional force, we're not given the applied force. But definitely, we're not asked to find anything that involves both. We're just asked to find the normal reaction. So we know we have our weight force always pointing down, W, and then the reaction pointing up, R, which is what we're looking for. So we know R must be equal to W, and R will be equal to mg. So what is my mass? 0.5 times what's my J? That's 10 meter per second squared, and this gives us 50 newtons. You can see how easy questions underneath this once you can analyze them. So let's move on to the next question. All right, so for the next question, we are told a block of mass M is equal to 6 kg is on a rough horizontal surface. The horizontal force F increases from 0 until the block starts to move at F equal to 30 newtons. When the block moves, the steady speed under the same force is V equal to 0.5 meter per second. I have to find the coefficient of static friction and also the coefficient of dynamic friction. So what we want to do, like we've been doing previously, is to make our sketch. So if we can make our sketch, we have a box like this in this direction. Okay, so my block weighs 6 kg. So I have my weight pointing downwards, yeah, and then have my reaction going upwards. So since we're told that a horizontal force F increases from 0 until the block starts to move at F equals to 30, so it means that my applied force at F equals to 30 is equal to my Fx maximum static friction. If I want to analyze or solve for the first part, I will simply say Fx max must be equal to mu x r. So I'll get my r, W is equal to mg, that's equal to r, and then what's my mass? Mass is 6 times 10, so that gives us 60 newton. So this is my r, 60 newtons. So let me clear this and then write it underneath our equation. So since r equals to 60 newtons, then we can say Fx mass is equal to okay, so again, let's clear this and then write, so clear this and then the Fx mass will be simply be equal to 30 is equal to mu s times my r, but you see my r now is 60 newtons. So mu s now will be equal to 30 over 60, so 0 cancel out 0. Mu s will be, so this is 0 0.5, that's 0 0.5, okay, so I think that's let's quickly press in the calculator whether that gives us 0 0.5. All right, okay, so not 0 0.5, so 0 0.5097, so 0 0.5097. So since it is unitless, then we leave our answer like this. So this is for the A part. Now for the B part, so if you read the question, we are told that my block is moving at a steady, what's it called? Like at a steady speed or constant speed. So we already know that when speed is constant or velocity is constant, it means I have no acceleration. So to analyze our question, so if my box is moving in this direction, in as much as it needs an F net to move in the direction, so we can say this is my applied force and my frictional force is coming this way. I can say applied force minus a frictional force Fk must be equal to F net. But F net is already 0. So Fa minus Fk is equal to 0. So why is it 0? Because my speed is constant. So if my speed is constant, so it means I don't have a change in speed. And if I don't have a change in speed, my acceleration will be equal to 0. So that's why my F net is equal to 0. So I can simply say my applied force is equal to Fk. So what's my applied force? We have it as 30. We have it as 30. So what's my Fk? So will also be equal to 30. But this time around, we're looking for the coefficient of static friction. So instead of writing 30 on this side, I'll just write what's it called? My mu k times r. So again, this will give us mu k will be equal to, so we already said 30 over 60, so that will give us 0 0.5097. So the reason why my mu s and mu k are equal is because I'm moving at a steady speed. If I'm moving at a steady speed, then definitely mu s will be greater than my mu k. So I hope this makes sense. So let's look at one more question before we look at the advantages and disadvantages of friction. Okay, so we're given a metal block of mass 5 kg lies on a horizontal surface or rough horizontal platform rather. If a horizontal force of 8 Newton applied to the block through its center of mass just lights the block on the platform, then the coefficient of limiting friction between the block and the platform is. So they're asking us to find the coefficient of limiting friction. So first we want to make sure whether we're dealing with questions on static friction or dynamic friction, because that will aid our analysis on this question. So we want to sketch first. So when we sketch, we have a block of mass being placed on a rough horizontal ground or surface like this. Now, the mass of my block 5 kg. So I know my weight is pointing down and then my R also going up. If the horizontal force of 8 Newton applied to the block to its center of mass, so applying a force of 8 newtons through its center of mass just lights the block on the platform. Then, so this is just slide. So we assume, remember when we were talking about our graph, so when it is just about to move, so we don't have an F net here. So we assume or we analyze this underneath static friction. So if that is true, I can say my frictional force F of S is acting in this direction. So, and then I can now say W is equal to mg, which is equal to R. So my m is 5 times 10, which is j, must be equal to R, and R here is equal to 50. So, and that's my R. And then we have, okay, so static friction must be equal to mu SR. And then since we're looking for the coefficient of limiting friction, so mu S will be equal to F of S over R, and F of S is given as 8 newtons divided by my reaction 50. So this will be equal to, so let me get the calculator and then see what our answer would be. So if we do that, we have 0.16. So another way to be sure if we're actually dealing with static friction or dynamic friction is to read the question. So we would know the applied force we are given, whether it will be a net force or not. So if you can remember the analysis, what we did initially when we were talking about the graph, and then if you apply that to various questions, I'm sure that you get the proper handle of questions underneath friction. So this is all I have for you guys today. Thank you for the time. Do well to like, share, and also subscribe to the channel, especially if this has been helpful to you to release so that release other contents regarding learning in physics. All right, so thank you.